Being as it is now 1:20, we will get started with the program. So I want to formally welcome everyone to the 2021 Georgia FRC Kickoff Mechanical Workshop. Today, as you might have seen in the broadcast, there are a couple different challenges for the game this season. But for this workshop, we're mostly going to be focusing on the skills you might need for the infinite recharge at home section of the program. Today, we're going to be looking at some common design challenges that you might face when building an FRC robot, and this could be for this year or even following years. And we're going to look for some audience participation to see what kinds of solutions you might pose for them, and then we're going to discuss common solutions to these problems. That way you can know what is typically done to solve these various design challenges, and maybe you can apply that to your robot this year and in following year. So with that, I believe we're going to start with materials, and for that I will hand it off to one of my my partners here.
Hey guys, Alex, nice to meet you during Kickoff. So talk a little bit about materials and materials are going to be used within your FRC robots, everything regarding that. So weight is something that's going to come into play very often with whatever you're building, whether you have weight limits, things like that. So it's kind of important to know which materials you should be using and when you want to approach them. Rather than go through a question, this one I'm just going to kind of explain the different materials that are very common to see in FRC robots and when they're applied and everything regarding that. Because when you're making your design, choosing the correct one is very important. So I'm going to the next slide. Talk about aluminum. This is the most common material you're going to run into when coming up with any design that you are going to have for your different robots. So aluminum, you're going to run into some common alloys, which are common types of aluminum, which is mostly 6061 and 7075. What these mean are, don't worry about the specifics. However, as far as strength-wise, 6061, the point of it is it's the most common you're going to run into. It is fairly light, so you're having lightweight, and it's much cheaper compared to steel. So that's when you kind of use that. Cons are it isn't as strong as steel, so you do have to do that kind of strength versus weight balance. And you aren't going to be able to weld aluminum at all. So if you wanted to weld anything for your robot or anything like that, you wouldn't really be able to use aluminum. As I said, the common alloys, 6061, 7075. 7075 is harder than 6061. But the main thing is when you are looking at what materials you're going to use, you can look it up if you're ordering a material to go get cut for you or something like that. You will see these as choices. So it's kind of important to not get lost in the codes, focus on these right here. Again, 7075 will be more expensive, it's a little harder. 6061 is the most common and the cheapest, so you'll probably be using that. And then I put an image on here as well of 8020. This is an aluminum extrusion. You're going to see a lot for a lot of FRC designs. It is very strong, and the whole concept of it is you can slide in different nuts, T-nuts, and things like that to help build whatever your design is. So you slide something into the track, and you can have something on there. That's kind of the whole thing of aluminum. It's a very good material, very common. Most robots you're going to find are built out of that. On to steel. So you're going to see a lot less of steel. The whole big point of it is it's super strong. So whenever you're making your design, you need it to support a lot of weight or things like that. Steel is generally what you're going to lean towards. However, it's very heavy. So what you're going to find is you need to use steel in a lot lower quantities with most of your designs. However, you can use it in these small weight loading parts of your design or anything like that. The other thing with steel is it is very expensive. But to kind of compare the strength, I put this nice chart right here on the right. So what that's basically saying is the way stress strain curves work, without going too much into it, the curve that you see when it like starts going horizontal, is when the material goes to something called plastic deformation, which basically means you can bend it and it's easy to bend. So it's kind of like plastic, you just bend around like that. So what you'll see is that chart is it takes a lot more force or a lot more stress to be on steel to get to that state than it does for aluminum. So, and steel can take a lot more. So that's kind of your example of what you're going to find there. And then they both, and steel fractures at much higher stress. Common alloys you're going to see for steel are A36, which is structural. So you'll find that on websites if you're ever ordering steels. You'll find that on there. 1045, a lot of screws and things will be in that. And then you have different stainless steels. So that's just something that you're going to think about for when you're making your designs for that. I know this section's very lecture heavy. It's hard to ask questions on materials, but yeah. The last material I wanted to talk to you about and just kind of explain before going into kind of the other parts of this is plastics. So you're going to run into a lot of plastics on your FRC robots. Plastics are light. They can be clear if you use a polycarbonate or plexiglass, and they're very flexible. You can do a lot of prototyping with different plastic parts or a lot of much lighter, quick things, or you can have more custom designs and a little more stranger designs. You can do that out of plastic due to how weak the material is. You're mostly going to see HTP, UHMW, plexiglass, and polycarbonate. UHMW you can buy in sheets, and it's good for like electrical boards and things like that. And then polycarbonate and plexiglass you can use for a light, clear side walls and things like that. So you'll see that come up a lot as far as material you can use. Again, it's very light and flexible, but it's much weaker than the material. So you won't be using it for support as much. You'll be more using it for like backing walls and things like that. So those are the three big materials that you are going to run into for designing your FRC robots. So whenever you're coming up with a design, just kind of think about what application we need. Do we need this to be super strong? Do we need this to be really light and flexible? Whatever the situation you need is, and that can dictate the material you choose.
As like an aside, you might also hear people refer to polycarb as Lexan, which is like a brand name. It's kind of like Kleenex to tissue. So if you hear anybody talking about Lexan, they're talking about this. Okay, so the next section is drivetrains, which are like, the core, the wheelbase of your robot. So oftentimes, this is the first thing that you end up designing on your robot. And there are a few different types that are very common in FRC robots, and I'm going to go through and explain some of them and their pros and cons. Feel free to make sure you ask any questions about any types of drivetrains you might have. So the first one, which is the most common, is the West Coast drive. So this is the kind of drivetrain that the KOP drivetrain, the Andy Mark 1, is. So that's a picture of it on the right there. It has 6 wheels and 2 gearboxes, or a gearbox on each side, each with 2 motors. So the main, it may just look like, 2 sides of 3 wheels, but the main thing that makes it a West Coast drive is the fact that the center wheel is what's known as a drop center. So the center wheel is slightly below the 2 side wheels, which causes some rocking, which has some interesting properties on the drive. So when you're driving in one direction, because it tilts slightly, only 4 wheels are ever in contact with the ground. And when you go the other direction, obviously it switches slightly. So adjusting the amount of drop center can change how well your robot drives in certain terrains. So if there's ever an obstacle or a barrier on the field that you need to drive over, increasing your drop center would raise the gap between the wheels at the front of the robot, allowing you to drive over it easier, but it would also make your robot more unstable because you'd be rocking more. So keeping the drop center in mind is important when you're considering these drivetrains. So some pros of this is obviously it's pretty easy to assemble. The KOP drivetrain is probably the best West Coast drive out there. The instructions are pretty clear. Easy to drive. It's similar to typically it's driven with a tank drive setup, so each joystick on each analog stick on like a game controller or two joysticks controls one side, so left one controls the left side, right one controls the right side. So most people driving robots are familiar with that. They're also easy to program. It's essentially just joystick to power on the motor, and they're very good for defense, which is something that a lot of teams sometimes neglect. But since they can only drive forward and backward for the most part, they're very hard to push perpendicular, and they're typically very strong, so they're very good at pushing. Cons, they're not the most versatile drivetrain, which isn't that big of an issue. If you're good at driving it, you can overcome this. And they only have non-lateral movement, which might not make much sense if you're unfamiliar with drivetrains, but in the next few slides, that'll make a lot more sense. So this is by far the most common drivetrain. Next is the mccannum drive, probably the second most common drivetrain. This one, you use what are called mccannum wheels in each of the four corners. These are a special kind of wheel that have rollers at angles along the circumference of the wheel. So you can see a picture of it here. You arrange your wheels in such a fashion where the rollers form an X in the center of your robot, and then this allows your robot to move side to side laterally if you power the wheels in a specific fashion. So the consideration here is obviously you have to power each wheel individually, because in the previous one, the West Coast drive, the left side and the right side were always, like, all the three wheels on each side were going to be going the same direction. But in the mccannum drive, sometimes the two wheels on each side might be going different directions in order to force your robot to drive sideways. So you need to have 4 different motors and 4 different motor controllers for each of the wheels. Pros, like I mentioned, it allows for lateral movement, and it's not too difficult to program, but it's definitely more challenging than the West Coast drive. Cons, it's very susceptible to defense, so these robots are usually pretty easy to push, especially perpendicular, because they don't have as much grip on the carpet. And as I mentioned, it requires control of all 4 wheels. The top of the slides here says most common holonomic drivetrain, and holonomic just means able to move side to side. Next is the H drive, which is also known as a slide drive. This is pretty uncommon, but you might see it sometimes. It's sort of like a cheaper way to do a holonomic drive. So you can see the thing that makes this a special drive is the wheel in the center. You can see the picture on the right. So all of the wheels on this drivetrain are what are called omni wheels, which are just regular wheels, but along the circumference there are rollers, but they're not as complicated as mccannum rollers. They just so this allows robot to, like, if it's pushed from the side, there isn't enough grip to stop it. So when this robot wants to move side to side, you can power the center wheel either going left or right, and then the whole robot will slide that direction. And then when it's just going forward and backwards, the center wheel, since it's also an omni, just doesn't stop it. Pros, this is pretty easy to assemble. It's just pretty much a regular 4-wheel drivetrain plus a wheel in the center, which you just position and then you need to power it. And it's a pretty simple holonomic solution compared to mccannum, which is a little expensive and a little more challenging to understand. Cons, this one is very susceptible to defense because none of your wheels have very much grip on the carpet, so you can be pushed from many directions. But if you're good at driving, you might be able to avoid that. It might lack a little versatility just because the center wheel is sort of like a point of failure. So if that goes down, your drivetrain becomes a little weaker, and it's pretty slow. So when there's only one wheel powered by one motor driving your whole robot side to side, it's not very fast. But that's not necessarily a huge drawback. And then finally, the Swerve, which is known as the holy grail of drivetrains. This is a very complicated drivetrain, which is very rare. I think there's only been 2 or 3 ever completed in Georgia. The way a Swerve drive works is there's 4 wheels, and every wheel is in what's known as a swerve module, of which there's a picture of here. And each swerve module allows the wheel to rotate 360 degrees as well as power the wheel. So when you wanted to go left, you would turn all of your wheels to face left and then drive forward, essentially, which in this case is left. So you can see this would obviously have like a huge, like, you can turn the wheels in different directions to do crazy spins and dodging people. And can be, if done well, can be very powerful. But the main drawback is they're extremely expensive. So every swerve module, on average, is probably about $200 or $300, which means you need 4 generally. So that's upwards of $1,000 worth of parts. They're very complicated. You can see there's lots of gears and belts just in this little module. And they're very challenging to program because you have to make sure all of your modules are always synced up and they're always, going at the same power so that you don't have some weird like shifted wheel things where you can't drive straight. If they're done well, they have both the benefits of mccannum, which allows you to go forwards and backwards and side to side, and the benefit of West Coast, which is not susceptible to defense, because if someone's trying to push you, you can just turn your wheels to be perpendicular and you won't be pushed. However, swerve drives are very rare and very expensive, but if done well, are probably the best drivetrain. And next is elevators.
For elevators, I actually made a quick poll that I'm sending right now on drivetrains. I want to get everyone's thoughts on this. I've never used the poll function. I just sent out a poll on the 4 drivetrains you just heard, and what do you guys think applies well for the at-home challenges that you're going to be facing this year? Where defense is less of a thing, it's more the challenges themselves.
All right, and meanwhile, I'm going to give you guys 30 seconds to give what you think would be a good solution to this problem. So, say you're starting this a new FRC season, not this season, just some season, and there's some kind of goal where you got to put a ball way up high. How are you going to take that ball and move it vertically by a great distance? What mechanism would you use to do that? I'll give you guys 30 seconds to write what you would do. And even if you don't think it's a good idea, if you think it's a bad idea, still put it in the chat. I'd love to get some laughs out of this workshop. And we'll give you 30 seconds to give you suggestions.
That's right, the two simultaneous things going on. As for the drivetrain poll, by the way, but most people seem to be going towards West Coast drive right now. mccannum has taken the lead. Okay. So we have 14 votes on that. Yeah, and one thing I will say is it's interesting with it being at home, looking at the pros and cons versus the importance of defense or not, because when you're at home, there's going to be, well, not really a bot defending against you. However, other drivetrains are bad against defense, good for lining up. However, when you're actually competing in the event, defense matters more. So it's kind of that balance to figure out for what you're facing this year. But right now, the most popular is West Coast and mccannum tied, and then H drive, we got a vote, and then no one has hit swerve. No one's bold enough to go for swerve.
Kind of funny because I'm not sure if anybody on the call knows this, but so I'm going to Georgia Tech, but I come from a team in New Jersey, and on my FRC team, swerve was always the biggest meme on our team because there's always like, most of us were all for the simple West Coast. There were always like three people on our team who were like, we need swerve. So it's kind of funny to see the same thing happening in the poll, but pretty funny. Anyway, I think we've gone well past 30 seconds.
I'm going to end the poll on drivetrains, by the way.
Yep, sounds good. Looks like a pretty good split between West Coast and mccannum. And I think that's pretty reasonable because
I think that makes a lot of sense because the advantage to mccannum, you can line up your shots really well, and it doesn't matter that it's the good defense. But the advantage of West Coast, easier drive to do, more classic, and really makes a lot of sense to do. So yeah,
there's a lot of information already out there.
A lot of variation to what you can do with your designs.
Yeah. Anyway, so in the chat I see some answers of elevator and two-stage elevator. Now, elevator can mean a variety of things, but if you want to move over to the slide on pulley type elevator. This is probably one of the most commonly used varieties of elevator, as you see, so much that when you say elevator, typically this is the kind you mean. So if you look at the image, it's a little small, but the way this works is we have this chain or pulley, probably usually a chain, or not a chain, but more of a cable that runs from the top or from the bottom to the top and back down to this little bar. And when you pull this cable in, it goes across a pulley on the very top and pulls this bar up. So when you wind up the cable on the bottom, it raises the bar up, and you can attach any number of things to that. You can attach some kind of grabber so that it brings up a ball and puts it in a slot. There are even probably ways you can set this up to lift your entire robot if you're careful. The problem with these is that it's kind of hard to bear the weight of a robot on cables like these, because obviously that's probably the weakest point in some of these situations. And when the robot's multiple hundreds of pounds of weight, or somewhere around there, then, plus game pieces and stuff, of course, then it becomes a little more difficult. And certainly, like I said, the capacity will depend on the tensile strength of the cable, and that's probably the weakest point of the pulley. And as you see in the chat, we have a 2-stage elevator. You can certainly attach these to each other. That way, if you have one pulley running, or the cable running from the bottom to the top, down to the bar, and then back up to something else, you can actually attach 2 of these so that it's almost like a telescoping elevator. And when you have something like that, you can get a little bit more reach out of it, because obviously with a pulley like this, or with an elevator like this, you can only go up about as tall as about as tall as it is when it's fully collapsed. When you have multiple stages, you can go out farther and farther, telescoping tire spyglass, for example. That's a really good answer, and like I said, it's probably one of the most common. Another type that we might sometimes see is a multi-segment arm. With these, they can be much more powerful because they're not going to be relying on just the tensile strength of a single cable. The way this one works is, and certainly Zach might be able to better explain this because I believe this is his bot, but because of the way these bars are linked together with gears right in the middle of that, or right in the middle of that joint, when you use a motor on the bottom to turn the bottom joint, it'll raise the entire arm at once. So that way you really don't have to, it's a lot more stable for one, because all the contact points are made of metal as opposed to some kind of cable. So it'll be able to raise a lot more load. However, it's not always, of course, the best option, because it might follow a strange path while it's extending, and so it's not always the best for all contexts, because of course certain types of elevators will be better for different kinds of raising. This one is much more strong, but it's much more complicated as well. With just a pulley, you just have a cable and a few rails and a cable. With this, you have many different pieces of linkages and joints that you have to maintain. And so in a case where you need to be, or in a scenario like FRC, where if you're in the competition, you're in the pits, and you have to fix your robot real quick because someone rammed into it and broke half of it off, which I wouldn't have any experience with, then it might be a little bit more difficult to do with a complex arm like this. So there's always trade-offs like that. Again, if you have any questions about what I'm talking about, or especially this robot in general, put it in the chat because we can explain it a little more. And one other...
Hold on, let me step in here. So this, since this is my robot, as Nicholas said, I just want to point out that some of the challenges we face with this one is that certain points of failure were very challenging to resolve. So we were talking about that joint earlier where the 2 segments of the arm meet and there's gears meshed together. Those gears ever shift or break, it's a real pain to fix it, because you have to disassemble parts of the bot and sort of readjust the gears and get them remeshed together. And if they're slightly offset, then you'll have some really weird stresses on your arm. So if you ever decide to build an arm like this, which can be very powerful, and it's easier to build a climber or something with this arm because it's easier to build like a higher load-bearing arm, keep in mind those sorts of points of failure where it might be very challenging to fix it in between a match.
Thank you, Zach. Another common type, or maybe this is probably not, I wouldn't say common instinctively, but an uncommon type of lift would be a scissor lift. So if anyone doesn't know how these work, if you think about a pair of scissors, when you close the bottom of the scissors, the blades of the scissors also move together. And because of that, if you string multiple of these scissor-type mechanisms together, you can create this accordion-style lift that will push a platform up and down just by compressing the very bottom of the lift. And of course, this is quite spectacular looking, and it's really fun to see in competition, and it's quite efficient. However, because of the way it's set up, you really need to be quite precise with how you build it, because with each of the bars, you need to make sure the joints are working well, and there needs to be very little play, because of course, the looser the joints are, the more wiggly the platform is going to be, because you have multiple of these scissor mechanisms that keep going up and any little bit of imprecision in the bottom one is going to be multiplied by however many segments there are. So with these, you need to be much more precise with your dimensions, and for that reason, it's not always the most recommended type of lift. However, it is certainly quite possible, and as you can see here, from many years ago, use of it in competition, and it can work well if you do it right. And moving on, so perhaps one of the final ones here would be using pneumatics or a piston. So with this, and some of you are probably more familiar with pneumatics than others, but by sending pressurized air into the piston, it'll extend the inner part of the piston out, which will increase the total length of the piston. Now, this is always, especially on my team, it's always been a bit of a meme, since back on my team, we never really liked to do pneumatics that much. But pistons can be totally useful, and they can be quite powerful, depending on how big the piston is. But there are a lot of drawbacks. You will need to have an entire pneumatic system, which might require an entire other, like if you have your electrical board, often you might need an entire other pneumatics board, and that isn't always the best, or that can add complications. You're going to need a lot of air tanks to store all the air for compressing. Another thing that we ran into, I think it was last year, 2 years ago, for getting onto the HAB platform I always forget the names of these. In
Deep space.
Deep space, yes. The problem is with the pistons, they're kind of all the way up or all the way down. So because compressed air, you can't just decide to put a little compressed air on one side and a little compressed air on the other. I mean, theoretically you could, but it's not an easy scenario. When you want the piston to extend, it has to either be all the way in, or when you put the pressurized air in it, all the way out. So this gives it a little bit of a inferiority to other kinds of systems, like even the scissor lift, because with a scissor lift, you can just put it in halfway, and then it can stay halfway up. And so for one thing, you can pick how high to go. So if you're ever in a situation where there are multiple heights you need to get to, pistons are probably not going to be the one you want to use. Additionally, it kind of makes it hard to synchronize them. So if you're just trying to use 4 pistons to lift your robot, like my team 2016 tried to do in a couple of years ago, I always forget the numbers for these things, but we had problems with we would send pressurized air into all the pistons at once, and then like 2 of them would go up first, and the entire thing would fall over. So not, as you might imagine, the most successful kind of lift when you do it wrong, like we did then. At that point, we found that adding the follower rails to the pistons helped them go up more consistently. At that point, we actually had pretty successful climb with pistons. So, like I said, with pistons, you also kind of need to do it right, kind of like the scissor lift. Not always the most suggested, because obviously things like the pulley system and the segmented arm can be quite effective and possibly more simple, but these are also quite effective when you do them the right way. I think
I'll add that pistons can be combined with the other elevator to various things. So like you could put one of these pistons at the end of a different lift, and if you wanted to use the piston part for climbing to give you like a small extension as well, for like a hook or something to grab onto it, that is a valid application as well. It's worth noting that a piston can only extend out a maximum of 2 times the size of it, because it's just the rod sitting inside of there and it comes on out, which means you really need the extra extension of height. You may want to combine some of these together.
Yeah, so what you're saying, like with the piston, it shares the same kind of issue as the single stage pulley elevator, that you have that limited extension. So again, you could theoretically put these in stages, or like you're saying, combine them with other mechanisms to get even more reach. Certainly. And I believe that's all of the most common types of elevators that you might use. So with that, I'll send it off to Alex with grabbers and actuation.
So I'm going to pose a question, see if you guys would like to give a solution to this in the chat. But let's say we have an object that is strangely shaped, like just there's not a ball or not a normal shaped object. What kind of device would you guys think is best and system is best to get around that object and like hold it? So if you guys are posting in the chat any ideas you have for a mechanical system that can be used to grab an oddly shaped object, give you guys some time to put something in the chat.
Give me 1 second. I'll set up a poll for the previous question, for the previous section. So just chill for a second.
Yeah, I wish I had an example of a strangely shaped object that I could bring up.
And we got the second poll posted in the poll section. Which of the, while you're working on the current challenge, what would you pick for elevator for this year's at-home game? Or even thinking about last year's game, which of course is much the same. Yeah. But I suppose at home versus at competition, you're gonna have different.
We have one answer of a claw or scoop so far. Claw, pneumatic, or elastic.
Keep those suggestions coming.
Yeah. Give it another 30 seconds to hear that, then I'll start going into the section.
Certainly, at home has a lot of different challenges to the at competition play, because at home you're not going to have any defense for one thing, because there's no way to defend. So perhaps for that reason, something like an H drive could be even more useful. Or like we're saying here, like the scissor lift, even if it is wobbly, you're not going to have anyone running into you and knocking you over with the scissor lift. So perhaps that's a little bit more attractive in this kind of scenario. Really interesting kind of question.
Yeah. All right. So I'm going to start hopping into the section actuations and grabbing items. To start off, I see claw is the most popular answer, and I'm going to talk a little bit about how you can set up that claw and actually actuate it. But first, I'll start with wheels as a system for grabbing things. So wheels for an oddly shaped object probably wouldn't work the best. This is mostly what you'll find for ball-shaped objects. But it's a broad category of motorizing some sort of round object to catch grip on the object and pull it inward to your robot. There are kind of two main types of wheel grabbing systems. The first being a horizontal bar one, as you can see above. So what you'll find is that often is like hinged or it can be pressed up to get around the object. The wheels spin and it pulls it inward into the main capacity of the robot. And one thing you'll also find is that on those designs you use mccannum wheels on the end. Because of the way the angled rollers are in, it angles it towards the center. So you can ensure that the ball you're grabbing is pulled inward. The other main type of wheeled grabbing device is one with horizontal wheels, like you can see in the bottom picture. So what you'll find is, again, they're a little loose or hinged or stretched off, but once it presses around the object, it uses the wheels to pull inward. Additionally, one thing you'll find with those, they often use compliant or squishy wheels for all of that to get around other objects. So whether it's a soft object or a hard object, it's able to do that. So that's what you're going to find as a very broad, common type of system to grab different objects. The next one to talk about is a rack and pinion. So this is, in a way, kind of like a claw or things like that of using a rack and pinion system. But essentially, how this works is you take your gear that has a motor on it, and when it rotates, it meshes with a long, straight bar of other teeth that are just like it. So when the motor starts going, it'll start rolling along this teeth system, and you'll see it starts closing together. So one thing you can do is you can take any fingers or hands that you have within this and start pulling in closer to provide pressure on whatever you're picking up. This was a system, I personally used this back in Recycle Rush to pick up objects. Some of the pros of using vacuum pinion systems, they're very durable and likely won't break. But it's got some problems, such as A, it is very slow. These things move super slow with going together. Additionally, if something can get caught or jammed in the teeth really easily, which will get it stuck. And then also, it is made of steel, so it is very, very heavy, so it'll affect your weight a lot. However, it is, again, a durable mechanical device. And also, in general, rack and pinions, beyond just FRC, is a very tight, common mechanical device you'll see like in industry things. Even if it's not as common for FRC things, it is a very popular system of converting rotational motion to linear motion. So if you wanted a linear grabber of some form, you can do that. So the next one I want to talk about is anything spring-loaded. So a lot of the guys who answered claw or elastic, this is likely what your claw will be actuated with, of some sort of spring system in there. So the whole idea is often they're used passively, where you have a spring on the end and then it presses around it and kind of stretch out and goes back on whatever object it's in. Or you can use another type of system where you put tension on a spring, and when you pull it away, it folds out. So you probably saw that in deep space a lot with how there was a design to grab the hatches. It would be triangular and it would open out. That's due to the spring loading that's on it from the pressure. Because what essentially happens is the object is putting the springs into tension, so they're pulling on them, and there is a force pushing back against the object, and that force holds things together. So if you wanted to build a claw, you could use springs to build this claw as okay, we have our claw device here, and the springs put pressure using the clawed ends to grab whatever object you're using. So these are generally very good to use springs. The only thing is you do have to come up with some mechanical device in addition to them to figure out how the pressure is getting set up. But yeah, so you'll find a lot of common spring-loaded actuation. The next one I was going to talk about is a pneumatic system. And yeah, so if you want to make the claw, as I saw in the chat a lot, you would likely use a lot of pneumatics for this. You could use a lot of pneumatics. Essentially, pneumatics are, as we talked about with the big piston, is using air to power different types of pistons or solenoids or any types of different devices. So what you'll find is you basically build an entire system of holding air together in tanks, and then you release that air into, let's say, the pistons or things like that to extend or retract the mechanical device. You can't really control much of it other than the speed of its extension. That's one of the downsides to it. However, it's very common, very good for providing strength to grab your objects or things like that. Another downside is you do need the entire pneumatic system. So if your only pneumatics is, let's say you want a claw that has on a hinge and you press against it with a piston to close in or something like that. If that's your only pneumatic system on your robot, it may not be the best to use because that is adding an entire system which adds a lot of weight for only that device. However, if you're using pneumatics in a lot of different places, then it becomes more or better to use because you aren't just creating an entire system for one device, you're creating the system for many different devices. And additionally, last thing I'll talk about is, since not only we made a slide for this, but you could also, if you just wanted to put a motor on a hooked shape to rotate around to get under something, you could do that, but that has a big problem of not having much control. So that's going to have a lot of similar problems to the pneumatic system, but it's going to be more rotational than linear, like a lot of the pistons. And I put an image of the pneumatic system on here. where you have a compressor that compresses the air, fills up in the air tanks, use regulators, as you can see on there, to control where things go, and then it controls which pistons do what. So pneumatic systems are very popular to actuate your systems that you're going to have. Yeah. That's kind of the big thing on actuation of just whenever you're coming up with a design and you say, okay, this is the mechanical idea of what we want to do with it. Again, I'll use claw as an example. That was most popular. I want a claw. You kind of have to think which of these actuation systems is going to make the claw move that works best for us. You kind of think about those different systems. So yeah, that's kind of what I have on that. And then I will make a, or do we have a, yeah, so I'll make a poll, or start that, for the grabbing system, which is what's the best one you would use for your at-home environment this year and for the particular objects you have in this game.
The next section is shooters, so similar to the last one, put in some guesses or sort of ideas for what you might use shooter-wise. It might be better just to give like a specific way of like how would you add speed to the thing you're shooting, which is in this case usually a ball. So sort of just try and give like a simple description of the shooter you might use in a game like this. I'll give you guys, 30, 45 seconds.
I will say it's still interesting to see the responses from these polls, because I'm seeing consistently probably the most simple option is being just the most. And I think and I don't blame you at all, because certainly on my team we've had a lot of success with picking the simple option. But I will also point out that if you're going, yeah.
I was going to say, one thing I'll add to that is there's a nice acronym that my mentor in FRC would always give us, which is KISS. Keep it simple, stupid.
Our thing, we got to change to keep it simple and safe, because I guess some.
Oh, is that what you got?
At that point, you just change it to KISSS. Keep it simple and safe, stupid. So it didn't really work.
Fair enough.
Anyway,
but
I think it's interesting to see that always a lot of the simple options being chosen. But I will point out that if you're going for something like the Innovation Award and these awards that are looking at your mechanical design, perhaps the simple option won't necessarily be the most appealing to the judges. I mean, if you can make it work really well, then certainly. But if you could also make a pneumatic system work really well, they might like that even better. So always something to consider. So I do like simplicity.
Yeah, but then again, simple is always good, and then the more components you do have, though, is also more areas things can break. That's the other thing. It's kind of, you increase complexity, you increase number of things that can fail. You kind of have to find that balance in all of your designs. So kind of when you're making a design, think about, okay, well, when I've made this, what do I expect might fail on this? What might not? And then kind of weigh the pros and cons. Because most of design work is looking at the situation you want, come up with an idea, and then figuring out the pros and cons based on the different mechanical systems that you know.
Indeed.
All right.
Maybe 2 more seconds and see if we can get any suggestions for the shooters.
It's okay if you guys don't have any ideas. Shooters are one of the more complicated topics, so if you're unfamiliar, it might be challenging to just sort of come up with something on the spot. So part of the point of this workshop.
We are learning.
All right, so let's take a look at some shooters. The most common, the shooter section is going to be a little different because there's really only one kind of shooter, which is one that shoots. So it's going to be more like different add-ons you can apply to a standard shooter. So the standard shooter is the stationary shooter, where you stick a thing on your bot and it has a tube connected to where balls are, and you spin a wheel really fast and it shoots the balls. So you can see in this photo, there's a motor on the outside, and inside there's a big roller or wheel. So when you want to fire a ball, typically, very rarely do you have to shoot an object that isn't a ball. You'll feed a ball up using some other mechanism, and then it'll hit the wheel, and the wheel will impart a lot of speed into the ball, and it'll fly forward. One important thing to consider is the spin of the ball. So, and you'll see in this example shooter, only one side of the ball is being propelled. So the top side is stationary, which means when it comes out of the shooter, it's going to have top spin. So it will be spinning like towards the shooter, if you know what I mean. Like if you're looking at it from the side, it'll be clockwise. So this means that the spin will allow it to gain height, which is what you want. If oftentimes the shooting targets are well above the angle of the robot, or just like the top of the robot, so you want to be gaining height. You want to have an upwards arc with your ball in order to score the balls. So that's why top spin is typically what you want when you shoot, so that they gain height. Oftentimes when designing a shooter, you need to do a lot of math to ensure that you're going to have enough power. The things to consider include the RPM of your flywheel, or the wheel that imparts the speed, the power of your motor, the size of the ball, and the potential spin. Now, spin is sometimes hard to account for, but sometimes some rudimentary math can give you a lot of clarity on whether or not your shooter is going to be powerful enough. For this example, the stationary shooter, it's the easiest to build. There's tons of examples online and that other robots have used in the past. And I mean, the most simple way to explain it is just a wheel that spins really fast. Easiest to tune. So oftentimes, like a procedure that needs to be performed with any shooter is tuning, so that you have the speed like locked in right at the right speed, so it's not too slow, so it's too low, or too fast where it misses, and the fewest variables to account for. So in this case, the only thing you need to worry about is how fast the wheel is going, essentially. The primary con to a stationary shooter is you can only shoot from a few spots. So because the angle of your shot is inherently attached to your speed, there's only a few locations on the field that you can shoot from, and it has to be pretty much directly in line with the shooting target. So in like a more traditional game, which isn't at home, unfortunately, would be like in person, if someone was to notice that you can only shoot from a few spots, they might go play defense on you, so then you wouldn't be able to shoot. So that's the sort of thing that you have to consider when building a stationary shooter. However, elements of the stationary shooter are in all shooters.
Yeah, and to add to that, when you're picking that type of shooter design, it's important to think about the interaction that it has with the drivetrain you choose. Because again, if you're in specific locations, maybe a West Coast, it's harder, it takes longer to move to that location. You want to use something more holonomic to get into the position that works for that type of shooter. So all your mechanisms throughout your whole robot kind of work together in different ways. Kind of think about that.
Next is the adjustable hood, which is somewhat uncommon, but you'll see it pretty often, and a lot of top teams use the adjustable hood. So what this essentially does is it allows the top part that the ball rides along that isn't propelled to adjust an angle. So this gives your robot many more positions to shoot from in line with the goal, because it'll essentially changes the angle that your ball leaves the robot from. So as I mentioned with spin, you'll be adjusting the amount of spin as well as the angle that it exits the bot, so it changes the arc that the projectile will follow as it enters the shooting target. So adjustable hoods can sometimes be a little challenging to build, and a lot of the mechanisms we've described, like sort of different parts of them, might play a role in actuating it. So for example, in this is a picture of Team 254's adjustable hood from a few years ago. You can see there's like a piece of metal with teeth in it, which kind of looks like a rack and pinion. So some of the stuff we said about rack and pinions might be applicable here, where they spin a gear and the hood sort of slides up or slides down. Obviously, you can see this is sort of something that goes in addition to the stationary shooter, because you can apply it and you'll have elements of both. So pros, as I mentioned, increased range and availability of shooting locations, and you can shoot sometimes, depending on how it's built, from very close angles, because you can lower your hood all the way and shoot almost straight up. Cons, sort of like a con with most shooter improvements, is it's harder to tune, because now you have another shooting variable. So when you're shooting, you have to make sure that the hood is always at the right angle, as well as the wheel is always at the right speed. So shooters get more complicated to tune as they become more complicated to build. And then finally, this is probably something everyone's thought of, the turreted shooter, or a shooter that it's possible to change the angle. So this obviously allows shooting from many different angles rather than just straight ahead or whatever angle your shooter is at. So this makes as Alex mentioned earlier, the West Coast drive much more feasible in a shooting robot because you can drive up and it doesn't really matter how precisely positioned you are because your turret can just adjust for any error you might have. So the big issue with the turret is the aiming. So it's very hard to aim directly at a target. Generally in FRC games, there's a vision target, which you can use to like line up using software, but that's usually really hard to program. So a lot of time when you're building a turreted robot, you need to consider how carefully you're going to be able to aim your turret because doing it by hand from the other side of the field is pretty hard. Additionally, it's pretty difficult to maintain sometimes. There's lots of moving parts, and you have to be aware that like cables or like wires and other things that go between the stationary part and the moving part might get tangled up or pinched in between gears, which could limit, like obviously would jam your turret and potentially break it. So all of these have to be considered when building a turreted shooter. However, if it is done well, it is very powerful and dramatically increases the number of places you can shoot from. And obviously, this is a photo from the same robot as the previous one. It's Team 254's robot 2016, which was very good. And you can see they have a big gear going around the outside of their turret, and that is what spins and it allows the whole mechanism to turn. And I think that is all we have for shooters.
I am going to add a couple of things on shooters as a whole, which is there are some much less feasible things that are theoretically shooters that can technically be done. Like if you wanted to build a catapult, that would be very difficult to tune, very difficult to control, and probably wouldn't work as well. But theoretically, it does launch an object. You can always come up with mechanical devices that can launch whatever you're doing, but these are the ones you're going to see that are most common because they work well. These are kind of what you'll find to make your shooters work well versus other things that are interesting.
All right, and with that, we'll move on to our final section before our Q&A, which is about shop tools and manufacturing. So the question I'll pose is, and it's more of a general one, what kind of tools do you have in your shop? Or what kind of tools do you think would be useful to help build or manufacture the various parts of your robot this year or in any year? And this could be something as simple as like a hand power tool, or it could be some kind of large shop manufacturing mill or something like that.
And also, I just started the poll for the shooting options, so make sure you guys get your votes in for that.
Yep. Kind of funny hearing you talk about the shooters because on my team, I've always been part of the group who is always like, no high goal, because on our team, we've always historically been like a low bot. And so often whenever we come to this decision of what kind of shooters we pick, I'm always saying just none and go for the other kinds of opportunities. And from what I understand, I think this year there are still multiple different ways to score things. You have the searching for the game piece, but also, of course, the multi-stage shooting, which I think I referenced in the poll question. So I guess it depends on what you really want to go for, because sometimes shooters can be complex if you've never really worked with them. That's kind of how our team was for a long time. Anyway, yeah, just the question that I was asking was, what tools do you have in your shop that you think you would commonly use for building a robot? It could be literally anything, because we're going to talk about quite a few.
Also, I'm curious about what the most complicated tool your team has access to is, in your opinion.
Yeah, because of course,
sorry,
you go.
I was saying, every team has different access to tools. It's kind of good to know where you are with that.
Yep. I'm sure if you're like sponsored by 3 different countries' space programs, then you might have these complicated, I don't know. I wouldn't know. I'm not one of those teams that's sponsored by 3 different space programs.
But not every team is Robonauts or Cheesy Poofs.
Yeah. So I see someone in the chat says milling machine and lathe. That's basically where our team is at.
That's more than my team ever had. Nice.
Never used a lathe in my life, so our team definitely was even lower than the mill and the lathe. However, you can definitely get by with just You'll see in this
Oh, yeah,
presentation,
certainly.
there's like only a few tools you'll need, and you'll be able to build a great robot.
Yeah.
Yeah,
My team never had a mill or a lathe. Yeah.
I think the
Although
reason,
those
the
are
only
very
reason we had
useful.
it was because, so the team that I'm from, Team 2016 out of New Jersey, we operate out of the New Jersey School for the Deaf, and because they let us use their, even though that's not the school that I go to, we're partnered with the nearby high school. The reason that we have access to a milling machine and lathe at all is because they let us borrow the tools in their auto shop. So that's probably the main reason we even have access to those kind of things.
Yeah.
So it's kind of nice.
Another response. You have a CNC router too. Goodness. Your team has a lot of good stuff. And then access to a water jet cutter at Tech. Yeah, there are a lot of places to get access to that. Now I wonder if I know who your mentor is, because he's at Georgia Tech.
It's me. Just kidding. That's pretty fun. I think we technically had a CNC at one point. It never really worked too well, from what I remember, though. I think we got rid of it. And we replaced it with like a benchtop second mill, which I wasn't a fan of. But
I have a friend whose FRC team had access to a really old CNC that used floppy disks.
Oh, that's fun.
So they had CNC. It was just interesting.
Sounds like it. All right, I think we're probably well past 30 seconds at this point.
Also, before we start, I was just to ask the group, does everyone here know what floppy disks are, or am I too old now? I just want to know where it's at.
I think we'll
you mean the thing with save? You mean the things that were designed after save icons?
Exactly.
Yeah.
All right, so we're going to get started with the shop tools portion. I think we weren't necessarily expecting people to have mills and lathes. We might even have slides for those, but we'll talk about those at the end. We'll start with some of the more basic tools, such as the drill. So if you're a craftsman here, you might see DeWalt or Makita, some other common brands for that. Very useful tool for designing robots. Obviously used to create holes, but also to drive in bolts with a screwdriver and that. Sometimes you can use those holes for creating joints on your robots. Use it for removing material, as I mentioned here, Swiss cheesing, which is the idea of cutting out holes in material to save weight. But drills can be, obviously it's a very base tool in your toolbox, which can be used for a lot of elementary operations, especially just for prototyping and stuff like that. If you need to test to see if some kind of arm swingy thing is going to have the path you want, you might just grab some 2x4s and some screws and a drill and put it all together and test it that way. Drill can be really helpful for prototyping. Moving on to next one, not really drill related. This one's a cutting tool. The brand name that you might see often would be the Dremel, but generally this is just any of these small rotary tools. The Dremel will come with many different kinds of tool attachments you can attach to it. The most common you might see is a cutoff wheel. So if anyone's not familiar with this kind of tool, a Dremel takes a small disc or a small brush and spins it at really high speeds. And with that, you can use it to cut off bolts if the bolt won't come loose. If you need to, especially like in the pits at competition, if you need to cut something off or if something isn't working and you just need to make it shorter, then that can be a really good use for it. Dremels can also have like stones and sanding discs added if you need to. If the judges come by or if the inspectors come by and they say, "Hey, your robot has a sharp point here. You can't be like certified," then you can take the Dremel to it and sand off that sharp point. And the Dremel is mainly, I think in my experience, mainly useful for emergency stuff. Often it's not really the best way to cut something because, as we'll say in a second, there's a lot more other options for cutting things in the shop. But when you're in the pits, the Dremel can be a really good thing to just kind of plug into the wall and turn on and cut off something that you need to quickly cut off. Moving on to the next one that we have, one of these cutting options that, again, kind of more of an emergency thing than I guess it depends on the tools you have, of course. But in my shop, it was more of an emergency thing. The jigsaw. If anyone's never seen a jigsaw, the way this works is it takes that blade at the bottom, and instead of spinning it really fast, it oscillates it back and forth really fast. And that allows you to cut any kind of, it allows you to cut more complex shapes. I mean, if you think of like a table saw, for example, it's going to make a straight cut, but say you need to make a curved cut, that a jigsaw would be useful for that, because you can just take it and bring it in a curve. Jigsaw can be useful for cutting any number of materials. If you think about, I mean, maybe the most common you might see would be plywood or wood, because, I mean, it's a saw. But it isn't just restricted to that. You can also use it to cut other kinds of sheet goods, so polycarbonate plastic, again, the clear plastic we were talking about earlier. Or even, I think, in severe situations, you can get blades that'll work for metal, and you can use it for like aluminum sheet or aluminum bars. The jigsaw probably isn't the most precise of cutting tools, but it will be fast if you have a fresh blade. And so again, good for the pits perhaps. But if you need to use it as like a main cutting tool, you cut stuff and then just sand it afterwards, that can also be a good way of using a jigsaw to get precise results. So jigsaw, I wouldn't count it out. Moving on to drill press. So if you think about a handheld drill, when if you're trying to use it and you want to drill in a very specific location, it might be hard to do by hand, because what if you're stuck to one side and then it drills it at an angle? A drill press helps you avoid all that. You see in the slide it says heavy duty drill. That's because these things be very large, made of metal. Often, the good ones can be like as tall as you or taller. The way this works is it basically holds the drill perfectly upright, and you can control how far down it goes with the little handle, I want to say, on the side. And for this can be useful, especially if you have, if you know that you want to make a sheet with holes exactly here, here, and here, then you can mark it out with a scribe, or even with just a marker, and then you can use the drill press to drill exactly there. And so drill press will create much more precise parts for your robot. So again, it's not necessary. If you only had a hand drill, careful about it, you can get pretty reasonable results. But a drill press helps you take that extra step forward to get probably more higher quality parts. As well, I suppose drill press can also handle much bigger drill bits usually. On my team, we had this massive 1 1/8 inch drill bit, which we'd use to create holes for bearings. And drill press is really the only thing that can handle that kind of giant drill bit. So drill press is a very useful thing to have if you have it. There are also some small drill presses. We used to be the team that would bring like a little benchtop drill press to our competitions, and people would sometimes come over to our pits to borrow it. So that can also be another option, even just for the pits, though maybe a small one. All right, moving on to bandsaw. You see in an image, we have two different kinds here. The one on the left is a horizontal bandsaw, which I have no experience with, but I know they exist. And the one on the right is the vertical bandsaw, which I do have experience with. So the horizontal bandsaw on the left is mainly used for cutting any kind of long stock. So it can be like a long bar, or I suppose even like a short sheet or something like that. But it basically means you can set it and forget it. So if you know you want to cut exactly here, you just put it in the machine and set the blade there, and then just maybe not walk away from it so it doesn't cause problems. But you can effectively stand back and it'll cut it for you. With the vertical bandsaw, it gives you a lot more, control, because so I suppose I should preface this with the way a bandsaw works. Is if you see, it's kind of hard to see in the video or in the image, but a bandsaw, as the name implies, has a long band that has teeth on it, and it runs those over two wheels, and because of that, it creates this saw that just kind of keeps coming right in the same location. So with a vertical bandsaw, you can use that blade and push things into it to cut it, obviously. And this is another example, it's kind of like a jigsaw, but a lot larger and a lot more precise because it's not going back and forth; it's just going around in a circle. So with a bandsaw, you can have a lot more control, like I was saying. You can push a say a piece of 80/20, piece of aluminum, into it and cut it in a straight line. Or if you have a sheath and you want to cut it in an angle, in a circle, in an arc, you can push it in and then just curve it as it's going in, and then you can have a much finer control with tight curves and stuff like that. So bandsaw, again, definitely not required, but it can be very useful, especially for prototyping. If you know that you need to prop something up at an angle just to test it real quick, you can run over to the bandsaw, take a piece of wood and just cut it at an angle, and boom, you have a wedge you can use for prototyping. So bandsaw can be a really quick way to cut any kind of material, maybe not steel, but any kind of softer material. And so that for that reason, it's a quite useful tool to get to know, and of course to use safely, but to use often. Anyway, moving on to the final one we have here is a water jet. Now, my team does not have a water jet, but we have it up here in case yours doesn't, in case you have access to it, like you were saying in the chat. But a water jet is a CNC type machine, which means the computer, you give instructions to the computer and it will tell the computer where to cut, which takes a high pressure water jet and blows it through the material. Now, it's not just the water that's doing the cutting, although you can get some really thin stuff to cut with just water. The way it works is there's a funnel which funnels in effectively rock powder. Usually we use some kind of garnet. But effectively, it's putting in really fine sand into that water. And so the water then accelerates that sand and ends up just hitting the material over and over with these tiny little sand grains, which allows a water jet to cut through any thickness of even like thick steels. So a water jet takes this jet and moves it around in any kind of pattern you want. So you can cut out really any kind of shape. So if you have access to a water jet, like we were saying at Tech, this can be really good for creating high precision parts because, again, it's CNC. So the computer gets told where to go, and the computer is much more precise than a human. And with this, you can create one thing that might be useful is sheet metal parts. So if you want to be able to fold a piece of sheet metal into a shape, like a box, then you can cut out the shape on the water jet and then fold it afterwards. Be a really good use for that. But water jet can really anywhere you need a much more precise part than maybe you'd be able to make on something like a bandsaw because it's computer controlled again. Anything you want to add to that? Because you guys might know more about water than I do.
I mean, I want to emphasize this last bullet point is very important. All teams in Georgia can access the water jet sponsor through KSU. So if you want more information, you can look at the GeorgiaFIRST website. But that means you can design parts that are water jettable, which are typically like aluminum sheet metal parts, and you can send them off. And then like a week or two later, maybe less than that, depends on how the build season is going, you can get the part back and use it on your robot. So This is a very powerful tool, and you can use it for many different robot parts, and they're typically very strong.
I will add that there are times, though, when you get the late in the build season where they will be backed up. So make sure you're getting your designs sent in as soon as you can if you really want those back. We get those designed and sent in quickly to use that. Otherwise, there are other companies that also offer water jet sponsorships if you track them down, but the big one is KSU.
Exactly. You definitely don't want to be sending off a water jet part like one day before your competition. But if you can get it in advance, then that can be a really good resource to take advantage of. And we don't have a slide for it because I think we weren't expecting people to have access to it, but we have the other ones that we mentioned in chat were the mill and lathe. These are machines, I'll talk about them real quick. These are machines that will also get you much more precise parts than you can get with any kind of hand cutting tools or even like a bandsaw or something like that. Because of the way that mills and lathes are controlled with kind of hand dials, so you can get much more precise dimensions. Or even if it's a CNC miller lathe, that'd be pretty cool. And I'm not sure if that's what you have access to. But if you did, that would give you even more precise parts. I won't go on too much, but lathes will help you to create circular parts, and mills will help you to create really parts of any shape, depending on how you can move the head, I suppose. Did you have something?
Yeah, to add to the mills and lathes, one kind of things you have an image of a mill. A mill is basically, the way I like to describe it, a big drill press that moves on the XY plane of the table, because you can move around in that. But one of the other big advantages to it is rather than just drilling with a mill, there are specific tools called end mills where you can cut horizontally. So essentially you pass it, if you have your part here, you pass it along and it takes off material and can cut pathways through the material. So that's something an advantage mills have because they can move to the side. Now that is not a requirement for a lot of FRC things you are doing. However, if you have it, you can design that in to be done. I just don't expect people to have that. And then lathes, all parts made on a lathe, or pretty much all parts, need to be done around an axis. So, again, if you're CADing a part to be done in the lathe, if it's done with the rotate tool on that, if it has no CAD things, that can be made with a lathe. But essentially, it's all cylindrical or circular things. Okay, there's a nice mill right there. So you can see those little dials on the side, moves the whole table. So it moves horizontally and you can cut things to the side. And then, do you have a picture of a lathe as well? We can get up there.
Look at it. But certainly some really powerful tools that you can, if you have access to, are definitely good to take advantage of.
How expensive are water jets is a question asked in the chat.
Depends.
I want to say $100,000. But let me confirm. I'm just Googling.
You're not going to get one for your home, for your shop, unless you get some kind of really big sponsorship.
You need a good, you can get a 2008 water jet for $80,000 right now. Ooh, I found one for $105,000. It's 2018, so a newer model that's used is going to be a little over $100,000.
Essentially, they're very expensive, so you should make good use of the ones that are made available to you for free.
If you want one from the 90s, you can get it for $40,000.
There you go. More affordable.
Here's a picture of a
yes. And that's what it is. So you can see the piece on the side. It's almost like if you took your drill press and you turned it on its side because it had the rotating part, except the other main aspect to it is rather than the drill bit or the bits on a lathe rotating, they're all stationary always, and the part itself rotates, and you use little cutting knives on the edge of it to cut through material.
Indeed. So I think that'll wrap it up with the tool section. Of course, everyone's going to have different kinds of tools, so feel free to continue putting in the chat maybe your favorite tool of the shop, if you have a favorite tool, or the most complicated or complex or dangerous looking tool of your shop. I don't know, anything that you might think would be interesting into the chat, because we're not going to put a poll for that. Meanwhile, we're ready. You can explain it.
Yeah, we're here to answer any questions you have on anything we've talked about today. If you want to understand something more, you don't think we explained something well enough, we're happy to explain something more and better. But as far as material to present, that's what we have.
Yeah, you can ask questions about the topics we've gone over today, or anything else about how to design a robot, perhaps workflow, any questions you have like that, because we've all been in FRC for many years, and so we have experience that we can transfer to you if you just ask. So we'll give you a little bit to post any questions. We'll hang out for a second.
Also, someone said looking at a Wazer in the chat, which appears to be a desktop water jet cutter for $8,000. I did not know that existed, but I did not know there was a desktop one, but that's going to have a really small build area for any parts you cut. So if you need any bigger parts, that isn't really going to be possible, but that is really cool. I did not know that existed.
All right, we got one question in chat. This is my first year in robotics. What are some useful tips you would give me? You guys anything you want to say about that? I definitely have something I can say.
Yeah, you can go first, and then yeah.
All right. I would definitely say this is kind of cliche, but whenever you're in a robotics program like this, you'll get whatever you put in will be. What's the phrase? I'm completely missing it. You get what you put in. I'm butchering that.
You get back what you put in or something.
Yes, I'm butchering that horribly. But the more you're involved in robotics, the more you're gonna get out of it. If you are just in robotics to come to every third meeting and then miss school for one day out of the year, then in my opinion, or not in my opinion, you're not going to get much out of the program. But if you really try to get involved, like for example, my team, we didn't really have much of a CAD team. So at the end of my freshman year, I helped design a battery cart for our team and taught myself SolidWorks that way. And just by doing that, I ended up changing my entire life path. Originally, in my freshman year, I was thinking, oh, I'm going to be a programmer. But once I got involved with SolidWorks, I ended up thinking, oh, I'm going to be a mechanical engineer. So
I did the same thing.
If you put in the effort, you might find great success in stuff like robotics. Because I learned SolidWorks on a whim that one time in freshman year, I ended up being probably like the most knowledgeable person when I came to my first CAD class in college, because I'd already been using SolidWorks for about 3 years at that point. So I was able to help my friends with the SolidWorks stuff just because I had learned so much from robotics. So the harder you work robotics, the more effort you put in, the better results you're going to get for yourself. So that's what I would.
Yeah. And to add to also other things, my biggest tip would be ask questions about what's going on. The biggest thing that being part of FRC and robotics is learning. All right, as much as it's a competition, everything going out, the important thing is that you're learning the skills you have. And you have mentors and coaches and older members who are there for that reason. So if you don't know something, don't feel embarrassed about not knowing something. Ask about it. Go to someone who you think might know, try to learn, and add that to your base. And then next year, when the new freshmen are here, hey, now you've already gone through those experiences, gone through those mistakes. You have the answers there, and you can help the next people. And you kind of this ever-ending chain of helping the people before it. So with it being your first year, just ask questions to all the people around you. And the other thing I would say is just have fun with it. It's really an amazing, unique opportunity that you get at this point in your life to go do that. And don't get so caught up in the stress and all of it. And just remember, you're here to have fun and to learn. And it is really freaking cool what you're doing. And you can show off to any random person, hey, I build robots. And you're already just up with how cool it is. So just enjoy everything that's going on. Enjoy what's coming to you.
Yeah, one other reason that I might say to ask questions is that not everyone, there are definitely some really great older members on the robotics teams, but not everyone is the best at relaying their knowledge to everyone. I know at least maybe this is only a my team issue, but sometimes on my team it's been an issue where the older members don't always take the initiative to really help teach the younger members, and that is not always a problem, but it can be a problem. And if it is a problem, the way you solve that is by asking questions yourself, take the initiative yourself. So I guess this kind of ties back into the more you put in, the more you'll get out of it.
Yeah.
Nicholas and Alex basically covered everything I was going to say. So.
Well, there you go.
Cool. Yeah. There it is.
So seeing no more questions, I think we'll probably end it off here. Unless we'll hang around a little bit longer.
Let's give it another minute just to see if anyone else has any other questions or comments or anything additional. We'll give it another minute or so. I'm
saying that we'll hang around a little longer for any more questions. But if we don't have it, we'll wait until about 2:45. If no more questions are at that point, we will stop the broadcast. But I want to thank everyone for coming out. Otherwise, because it's great to see that you're. For anybody who's new, great to see that you're joining the team. And to anybody that's returning, great to see that you're still involved in this great program. And I hope everyone has a successful year and that everyone stays safe as we try to navigate this wacky new format of the program.
Yeah.
Now get to work. Do that design.
Thank you guys for coming.
Yeah. Yeah, my team, this is the point where we'd all go off into separate rooms and start reading the rules for like an hour.
And then you
Yeah,
order a
I would-
pizza, get a pizza box out right on the back of it with a Sharpie.
Recommend
Accurate.
just read the manual. You'll make everybody happier if you read the manual.
Yep.
Yes, please read the manual. If you read the manual, you know it, and you're gonna come to the meeting and half the people didn't read all of it, and you're like, I did and I know it. Oh, you're already up there.
Yes, that's
Yeah.
the best advice for kickoff is to read the manual.
The coolest part,
100%.
in my opinion, at least it maybe depends on how all teams do it, but on my team, we always split up into different groups who will read the rules, and what we try to do is try to look for loopholes in the rules and try to find. Not like we're trying to cheat, of course, but we're trying to find ways that we can utilize the rules to our advantage. And often, by just reading the rules, it'll completely outlaw certain strategies that we want to do. I think one year we wanted to like lift off the ground on some posts or whatever. Like we wanted to try. I think it was deep space for climbing, and we wanted to try. We were thinking, oh, what if we just try climbing by just raising ourselves up in the air, but don't actually go anywhere? Would that count? And the answer is no, because we couldn't be touching the ground. So it's important to read the rules for stuff like that to know what strategies are even valid in the first place.
Yeah. Also, sometimes you do find a loophole that's like, oh, the rules don't outlaw this, and you start working at it, and then they send an email out saying first updates, and the update that they've now outlawed it.
Game update 1. Doing that is now banned, and you're like, oh darn.
Yeah. So to avoid stuff like that, you want to read the manual and be the one that sends out those requests saying, hey, is this legal? Because then you'll do everyone a favor by giving them the bad news early.
Well, I think that's all we have to say. So thanks for coming, everybody.
Yep. Good luck with your rules reading and your robot designing and your learning.
And your Infinite Recharge 2 season.
Yep. And your hand washing. Social distancing.
Yes. Mask wearing.
Stay separate, Danny Downer. Downtown Danny. What was it?
Downtown Danny.
Downtown Danny.
All right.
All right,
Stop
bye.
the broadcast then.
Yeah.